In the last video, we talked about breadth first search, which can actually be used to find the shortest path in unweighted graphs as well. And let's now have a look at another graph traversal technique that has exciting applications as well. And this one is called depth first search. Depth first search, also called as DFS, is another graph traversal technique which starts at a source node or a root node, and it goes as far as it can go down a given path, like depth wise, and then when it doesn't have any other nodes left, what it does is it backtracks and until it can find other unexplored paths, and then it again goes and explores that depth wise. So this is basically a depth wise exploration, while BFS was like more level wise or breadth wise exploration. So this has applications in backtracking. Backtracking also, if you implemented backtracking, you'll know that it does use DFS as well, and you just had more logic to prune your search space, but it does involve pretty much DFS. And then it's also used in exhaustive searches, like where you have to like try going as far as possible and to see something exists or something like that. So it's in all when you have to check for all possible paths. So we use DFS. So this can be implemented using a stack data structure, and that is last in first out. And the difference was BFS breadth first search used a queue data structure, while this uses a stack data structure. And since it uses a stack, we can either implement it explicitly using a stack data structure, or we can pretty much use like recursion to do it as well, like which makes the code a lot simpler. Though you'll have to make sure the edge cases are handled, or you're just going to have memory overflow issues because of incorrect implementation of recursions, because recursive algorithms are easier to run into infinite loops. But the pros are that it's much easier to code, and in fact you can just be done with like very few lines of code. So that is what DFS has to offer, and let's look at it with the help of an example. Note that the recursive approach also uses a call stack. So even though we do not explicitly initialize a stack, as in the case of the iterative approach of DFS, iterative code of DFS, a stack is used as well, even in the recursive version. It's just that we don't have to explicitly do it. It's handled by the call stack. So let's have a look at the non-recursive version, and then after that we'll also see the much simpler recursive DFS code. So here's a rough pseudocode. You can pause the video to let this sink in, but here it is. Initialize like a stack, yes, and then we mark all the nodes as unvisited. So visited of false, we'll set it to visited of every node, we'll set it to false, and we push the source node onto the stack, and then while the stack is not empty, we start popping the elements from the stack one by one. So the elements are popped from the end. So basically, pop of stack and pop of the element that's popped, let's call it u, and we'll basically be printing u for the DFS order. And if it's not visited, if it has not been visited already, we mark it as visited. Visited of u is equal to true, and then we explore all the unvisited neighbors of u, and we push all those unvisited neighbors onto the stack. And this procedure just goes on and on until all the nodes have been visited. So until visit of u has been set to true for all the nodes. So this goes on and on. So that is the pseudocode. Let's try working it out with this example. Uh, so initially I'll be putting 1 into my stack. So I'll be adding 1 to my stack. Then I'll be popping 1. And on popping 1, I'll be like basically printing that as well. So let me print 1, and let me print 1, and I'll mark 1 as visited. And then from 1, let me try like adding all the unvisited neighbors of 1 onto the stack. So that would be 6 and 2. And then now I pop 2 from the stack. I write it down. I write it down, and then I mark it as visited. So 2 is visited now, and then all the unexplored, unvisited neighbors of 2, I'll be adding onto the stack. So 1 is already visited. So the only unvisited neighbor from 2 is 3. So I'll be adding 3 onto the stack. And now it's time to pop 3. I write down 3. I mark 3 as visited. And then all the unexplored, unvisited neighbors of 3, I'll be adding onto the stack. So which is 7 and 4. Sorry, not 7, just 4. Just 4. 4 is one unvisited neighbor. The other one is 2, but it's already visited, so we don't add it. So then we pop 4 from the stack. I write that down. I mark 4 as visited. Now I'll be adding 7 and 5 as they are the unvisited neighbors of 4. So basically 7 and 5. Now it's time to pop 5. I write down 5. You can just try pausing and see that I'm just following these steps until all my nodes have been marked as visited. So basically, after I print 5, I just mark 5 as visited, and I'll also add all the unvisited neighbors of 5. Nothing is left because 4 is the only neighbor, and that's already been visited, so there's nothing to do here. And then I just pop 7 now. I write down 7. And I mark 7 as visited. All the unexplored neighbors of 7 I added to the stack, so which is just 8, just 1. And then I pop 8 from the stack, and then I write down 8, and I also have to mark it as visited. So 8 is marked as visited. So and then after I mark 8 as visited, I also add all the unvisited neighbors of 8, which is just 9. And let's pop the last element of the stack. I mean, there is 9, and so I write down 9 after popping it. Then I also have to mark 9 as visited, and there you go, done. And all the unvisited neighbors of 9 I need to add it to the stack. There's nothing left, and then we come back to 6. So as you can see, the stack we're maintaining allows us to backtrack, like, essentially. And so now it's like we found a way to come to 6, like backtrack to 6, and try finishing the unexplored portion from there. So basically, like 6 is going to be propped from the stack now. We do the exact same thing. I write down 6, and I mark 6 as visited now. And I also add all the unexplored neighbors, unvisited neighbors from 6. There's nothing left, so there's nothing to do. And now my stack is empty. I'm done with the procedure. And as you can see, all the nodes here have been like visited completely. So 6 was the last neighbor that was marked as node that was marked as visited. And there you go. So this is basically the DFS order. So this is the DFS print order. So that is 1, 2, 3, 4, 5, then 7, 8, 9, and then finally 6. So as you can see, it went depth first. So basically, it went as deep as possible all the way to 5. Then some backtracking, and then like it went, it explored 7, 8, 9 again depth wise, and then it just explored. It had to explore one last node that was left, that was 6. So this is an example of the iterative version of DFS. We'll have a look at the code walkthrough, and we'll also see the recursive version of this as well. So this will be a quick code walkthrough of the iterative version we just described. So I'm having a visited, which is a default dictionary that has been set to false. So all the nodes initially have been marked to false. And so while the stack is not empty, I'm popping an element from the stack. Then if that element has not been visited already, then I mark that element as visited. So visit of u is equal to true, and then I actually explore all the uh, unmarked neighbors, that is unvisited neighbors of that popped element u. So basically, if that v, let's call it v, the neighbor of u, and if v itself is not visited, I add it to the stack. To stack dot append v. So essentially, I'm just popping an element here from the stack, and then I'm exploring all the neighbors of that popped element, and provided that element itself has not been visited first, and then after that, like, I explore all the unvisited neighbors of that popped element, and then uh, if that element has not been visited already, I add it to the stack. So let me try printing it out, and this is the exact same graph uh, from the previous slide. Let me try printing the nodes. So as you can see, the order may be slightly different, but you'll still be able to see that this is actually going in a depth first manner. So 1, 2, 3, 4. Then 4 is connected to 7, so we can explore 7 as well before 5. So 7, then 8, then 9, and then after uh, explore 5 next, then finally 6. So even though there may be slight variations depending on how you add things to the stack. So depending on the order in which you store the neighbors and add them, the order may be different, but it's still the fact here you should be able to appreciate is that it's still in a depth first manner. So the exploration, I guess, like, you can try printing out how the breadth first exploration would be. So like you'll be able to appreciate the variations of when you're exploring depth wise and breadth wise. And let's now try to implement the same DFS, the recursive version now of it. So what would that be? Essentially, I need the same thing. I also need the visited dictionary here as well. So what I have to do here is just this: if the node is already visited, I just return. Else, I mark the node as visited, and then I also have to print the node. Then and I explore all the neighbors of this node. And if it's already visited, so this line will take care. So this is the recursive bit we're talking about, and that's it. Let's try printing it out right now. And I'll start with node 1, and then I'm also going to pass in a visited dictionary. So that's going to be visited, and let me initialize that again. So we visited, let me just set it to false. And let's try running this recursive code. So g.dfs recurse, I'm calling from 1, and let's try seeing what the output is going to be. So for the recursive DFS, it's actually exploring 6 first, and then we have pretty much the same thing. We have 2, we have 3, then we have 4, then we have 5. Okay, it's going to the 5 direction instead of 7, and we have 8, and we have 9. 1, 6, 2, 3, 4, 1, 6, 2, 3, 4, then you have 5, then you have 7, then we have 8, and we have 9. And for the iterator version, we had 1, 2, 3, 4, 7, 8, 9, 5, 6. But the point to observe is that both are depth first search, valid depth first search orders, and you should be able to appreciate that. So as you can see, I haven't explicitly maintained any stack here, but this will be handled by the call stack, the recursive call stack, and the code is much simpler in the case of the recursive DFS. And in case like our graph happens to be not connected, so let's say there are some disconnected nodes as well. So what you can do is you can basically run a loop for all the nodes in the graph, and then like you have to like call a DFS for every particular node, and so basically it'll explore all the nodes that is possible from that node, and this can be repeated and by keeping track of visited for the entire graph as well, and the same code would just work. It's just that you'll have to iterate over all the nodes, and then you have to start the DFS, the DFS function for that particular node, like for every particular node if it's not visited. So that's that. So that was the code walkthrough of DFS.